As mentioned, my name is Admir Mustafic. I work as an embedded engineer at IRQ Design and part-time as a teaching assistant at Faculty of Electrical Engineering here in Tuzla. The topic of my presentation today is to present the common problems and challenges occurring in automatic inspection systems and how to overcome said challenges. Usually in said systems we have objects that are in motion. Usually that motion is fast, and conventional inspection of those objects is not plausible, especially for humans. Even conventional systems struggle to effectively capture these objects properly. The conventional systems, the traditional ones, use just the stroboscopic-like devices with the periodic PVM light pulses, but lack the digital imaging post-analysis to really output the digital image on the end device. Also, we have another issue along with the stroboscopic effect. We have the rolling shutter effect, which most classic cameras suffer from this. So, first we have the stroboscopic effect, which occurs when we have a periodic motion of some object that is illuminated by also periodic light pulses. Usually pulse width modulation is used when the frequency of these light pulses is not matched to the frequency of the motion in case, like a rotating wheel, we'll have the exhibits of a stroboscopic effect, which we can see on the next video. So, can we play the next video? And here, as we increase the frequency of the light pulses, we see the effect of the stroboscope, where we have the so-called wagon wheel effect. The rotation itself seems like it's off and moving backwards instead of its natural motion. And also we have the distorted image, so it is not valid for our automatic inspection control systems where precision is mandatory to inspect, for example, objects on a moving conveyor belt. And next, we also have the issue of the rolling shutter, which most classic cameras have, but we also have the global shutter, which is present in some cameras but at a higher cost range. The main difference between these two modes, the rolling and global shutter, is how the lines are read. The data or the image lines in the rolling shutter are read row by row, sequentially in essence, whilst in the global shutter the whole image is exposed in one camera cycle, so the whole image is captured. Can we play the animation which will exhibit this? So, whilst the rolling shutter goes row by row, we have sampling at different discrete times, whilst in the case of the total or global shutter, we have the capturing of the image instantly. All of the photodiodes for the pixels are pre-charged and are ready for the exposure and ready for image capture. Okay. How do you approach to design a system that will be capable of capturing such images or to mimic a global shutter whilst having reasonable cost components? As mentioned, many cameras in the lower cost range do not have the global shutter effect since their architecture is much more complex than the classical rolling shutter. The example of one such system is to have an ARM-based Cortex-M7 microcontroller chip with the capabilities of the digital camera parallel interface coupled with the DMA. We have the digital imaging sensor, or our camera, which also has that capability to be coupled with the DCMI peripheral of said microcontroller with the pixel data lines, the parallel data lines, the horizontal synchronization, vertical, and the pixel clock itself. The storage of the data itself needs to be also really fast in order to ensure quick and fast capture, so we do not miss any frames. In that regards, we use the DMA coupled with DCMI and some external memory. In this case, SDRAM was used at, for example, 110 megahertz. And the key component is the synchronization signal, which is just a pulse train that is defined from the sensors themselves or encoders from the conveyor belt, for example, or some rotating wheel. This synchronization signal will be the trigger itself for our system when the capture will occur. And also we have the means of transmitting said signal to an external interface such as a PC, to some, for example, Python app via the Ethernet module, which also needs to be efficient and fast, so we do not have the overlap of the frame buffers, so we can transmit almost in real time our image. So pretty much here we have an example of such systems. For example, a camera used was from the OV564 family. The specifics of this camera is that it has a Frex mode or global reset mode, which mimics global shutter mode. It is still a rolling shutter camera, so the problems that we have with the classical cameras still occur. Each data is read row by row, so we have such a timing offset where we will have the jello effect or the distortion, and the object will not seem static like it's supposed to, like in the global shutter example. As mentioned, the Frex mode or the global reset mode is a special command in this family of digital imaging sensors, the OV564s, where the Frex request is sent so that all pixels, or for the photodiodes, are pre-charged. So even though the data is read still sequentially, all of the photodiodes are pre-charged so they can be appropriately captured and stored. As mentioned, we need to pair this digital camera interface with the DCMI peripheral itself in order to ensure proper capture of the image, and also with the hardware triggers, since synchronization is key. If it is a little bit out of sync, we will not have the proper global shutter effect. As mentioned, using the DCMI camera interface, the DCMI peripheral captures the pixel data on parallel lines. We have the possibility of 14 data lines, but usually we use the 8-bit parallel data lines paired with the hardware synchronization of the horizontal synchronization, where we have horizontal blanking between each line, and the vertical synchronization, where we have the vertical blanking or the indication at the end of every frame. And the pixel sampling clock itself, which needs to match the camera's pixel clock. In our example, it was set to 80 megahertz. The next step is to ensure proper data collection. In that regard, we use the DMA, which will pick up the data from the DCMI peripheral itself to the SDRAM buffers. For this to work efficiently, so we have the proper data capture, we need to have double buffers. Why? We must ensure we have no dropped frames. Synchronization is key, so in that matter, we need to have deterministic captures and processing times in order to ensure the proper synchronization and that there is no data overflow and such. So we, for example, use buffer 1, which is constantly filled by the DMA, and buffer 1, which will be transmitted via the internet to our PC app. Here we have an example, a timing diagram, where we have on the first image, the image capture itself. Whenever some data is ready, the DMA will pick it up, and that will be transmitted to the image buffer 0 or 1, depending on the current target of the direct memory access peripheral. And on the next timing diagram, we have the synchronization signal, the mentioned external hardware trigger, which will indicate when to start the capture. So this is the key signal which will indicate when the camera should start processing the image and sending it to the server. Once the image is captured, we can transmit it to the server, and the system is ready to capture another image. In order to achieve this, we need to have a chain of interrupt-driven events to ensure that every frame begins at the exact same time. Even if we have a small difference in time, the timing variation will have the skewing or blurring effect. So we will not, in the end, have the global shutter. To ensure this, as mentioned, we have the external trigger inputs, which can be just a periodic pulse train, the censoring image, or the sensor from the conveyor belt itself, the frame rate or the revolutions, and in the form of an encoder where the user can also define the offset of the capture itself in pulses or in time itself, for example, in microseconds. And we need to ensure at every DMA interrupt the transfer complete. When each pixel data is captured, the transfer complete interrupt is triggered by the DMA. We need to reset the internal state before each frame and switch the buffers to adequate addresses. And here we have the simplified state machine. The system is at the start in the idle mode, where it's waiting for this external trigger. Once it's received this trigger, it needs to validate this trigger. It needs to check its FPS. Why does it need to do this? Well, the maximum frame rate is defined by the pixel clock and the amount of data per bit. So we have, for a certain resolution and data width, we have the maximum frame rate we can capture. If the frame rate of the external synchronization signal, for example, a rotating wheel, is much faster than the maximum frame rate we can handle, we cannot capture such an image, since during the capture procedure itself, the image will become corrupted and we will not be able to send it at a proper time. In the other case, if the FPS check is okay, we can check for a delay. This is just added for a user that can delay this periodic capture of the image. And then we have the flash pulse function, which is just a timer peripheral, the PWM signal of the light pulses, and then we prepare the buffers, reset the capture state machine, and start the capture itself. While the DMA is capturing those pixel data, we'll wait for the DCMI frame interrupt, which will indicate the end of one frame. And once it's ready, we can start the transmission to the Ethernet, over the Ethernet to some PC application or whatever end device. Once that is done, we'll wait for the next trigger, which will be again periodic, ensuring the global shutter effect. as mentioned in the previous state machine, the main key is the hardware trigger. This trigger needs to be stable, so the sensor from the conveyor belt needs to be stable. If it has some time variations, our synchronization signal will also have those time variations, and we will not have the global shutter effect. Effectively, we'll capture images at different instances in time, not at discrete time points as we ought to, so we can have the proper global shutter effect. As a result, we will have the capture frame at our well-defined periodic moments, which is exactly what we wanted, and the image will seem static. We'll neutralize the common issue with the stroboscopic effect and the issue with the rolling shutter cameras, which produced skew, blur, and distorted images, or the jello effect, for example, on the propellers of the helicopter, which seem distorted, unnaturally distorted. So, the DCMI peripheral and the camera itself have the capability to capture JPEG images. JPEG images in themselves are smaller in size than raw raster images, and they are more suited for transmission via the Ethernet, so that saves us a little bit of time. So a natural question arises, why don't we use JPEG in this example when capturing the image? Well, one thing is that we must look for the start and end markers to determine the exact size of the JPEG image. But what about compression and decompression time? Here we have an example of the DCMI JPEG capture, where the vertical synchronization is determining the start and the end of the frame capture for one JPEG frame. But the JPEG packet sizes are in themselves programmable, which leads to variable blanking periods between each lines and between each rows. And the one thing we have with the variable packet size, we have usually some padded data if it's not aligned to 4 bytes, or if it's not, if the frame capture has prematurely ended, we do not have this full programmed JPEG packet size. DCMI peripheral will pad this packet with zeros. So why not use JPEG? Well, let's look at these 3 images. These 3 images are very similar. They have the same resolution, and upon first inspection are pretty much the same. The lighting only is a slight difference, but let's look at their encoding times, their compression times to JPEG. We see for the first image, we have a time of 3.123 milliseconds. For the second image, 3.016 milliseconds. And for the third image, 2.74 milliseconds. So, at first glance, not too bad. But if we have a conveyor belt, for example, at 12,000 RPMs, it has a rotation time of 5 milliseconds. And thus, it has the rotation time of 13.8 microseconds per 1 degree. So, the smallest difference here is around 107 microseconds. So that's already 4 or 5 degrees that we have. These variations will accumulate over time whilst we capture the JPEG packets. They will accumulate. Even minuscule variations will cause a drift in the image, and the global shutter effect will dissipate, and we'll see the image being slightly distorted, as in this next example here. On the left we have the good frame, where we do not have any distortions, and on the right we see that exact issue with the JPEGs. The frame is distorted, So on our view, we cannot properly see the marker, and we see it has the jello effect. It's not naturally aligned on the rotating wheel as it is supposed to. So up next we have a video where we'll showcase our system. So can we start the video? Thank you. Can we pause the video before at the beginning? We're out of sync a bit. So here we have the live system where you have two rotating fans. The first one you see is the one that outputs a synchronization signal. So we should expect a static image of this fan, whilst the other one is just as a reference to see the the rolling shutter effect and the lack of synchronization itself, and the importance of the external synchronization signal itself. It's not visible in the frame here, but we are using the STM32F47 discovery board, which all our students love, to produce the encoded hardware triggers and the offset itself. So can we continue on with the video? The board via Ethernet is sending to a custom Python application the image itself. If you can observe in the window, the outer fan is rotating, whilst we have the static image on the first fan itself. We can also configure the trigger itself, whether to be as a quadrature encoder in pulses or a periodic pulse train. We can continue on with the video. Yes, here, as we mentioned, we use the Discovery 407 board. And as such, we have accomplished the static image itself. The manifestation, like the image, is frozen, so it is usable in such automatic inspection systems, even though the camera itself would produce the rolling shutter effect. And at the end, that is how I eventually learned to stop worrying and love the global shutter itself. Thank you, that's all.
Thank you, Admir, for this great presentation. And you know the drill. If you have any question, please raise your hand. And our Mirza will give you a microphone. We have one question in first row.
Hi, great presentation, thank you. One question regarding the ping pong buffers that you mentioned.
Yes.
It's a great thing, but everything afterwards needs to be really time deterministic. Everything needs to fit in a time for the ping buffer to fill in again. So how did you measure that? Or other choice would be a FIFO buffer. So how do you know that you don't need a FIFO?
The one thing I may have failed to mention is that we have the constant reallocation of addresses. That's why we use the SDRAM. We cannot just use one buffer. That's why we need double buffering, or we will be constrained by the image size itself, and thus the synchronization process itself will be misaligned, if that answers your question.
Yeah, thank you. If it wasn't enough time for a ping pong, you will have a FIFO, right?
If it was not enough time to transfer the data, the data to the buffer itself.
No, afterward.
Afterwards, well, we would need to have a FIFO buffer, but there still remains the question of when to transmit that image. Will the next image come before the transmitting or after? And will the Ethernet itself be capable to transmit that image in time? So we do not have data compression. The FIFO buffer will then, every FIFO buffer will eventually be overwritten at some point if the timings are off.
Okay, thanks.
Admir, thank you for an interesting presentation. Your talk was great. I have a question regarding the validation of system which is complex as this one. So how do you approach validation? How do you ensure that all the operations you mentioned, which have really strict timing requirements, are done in time? So that's my question. How do you validate a system such as this one?
To be quite frank, it was a bit complex, but each step of the way, from the camera capture itself to ensure that the image capture is well timed and not prolongated. So essentially validating the pixel clock itself and the speed of the image capture. Then afterwards, we need to validate the hardware synchronization. Essentially, it boils down to using an oscilloscope quite often. And then at the end, we will see the end result on the Python app, which is the only true valid, let's say, validations. It's analyzing image buffers and knowing it's the proper image is not really feasible. We can validate, for example, the period of the sync triggers themselves, which once again boils down to the oscilloscope and the timing of the interrupts. So it boils down to a lot of debug messages and using the oscilloscope.
Okay, thank you.
Hey, Admir. To help, provide additional information for Amar's question. So the thing is that the question is very valid, and for the future engineers, someone who wants to work in this area, it's very important to understand this question. It's not just to do the measurements; it's to know how to make them. And in this case, and this is really beautiful case, like Trump says, that you cannot place breakpoint. You cannot place breakpoint. So this is just what I wanted to, add additional context to Admir's, information. So we cannot add a breakpoint and see what's happening. This needs to be orchestrated in a really synchronized manner, and the only way to measure something, even placing debug messages, can introduce delays and false information that will lead you to incorrect conclusions. The only way is to using external instruments, basically, and flipping GPIO pins when certain operations starts and stop in order to, so additionally, just. I know. No. Okay. Yeah.
It essentially boils down to validating each step of the procedure rigorously, since if it's one part of the system that's off, the whole system shuts down, and you have to look where's the issue, how to find it, and how to correct it. What even is the issue? Okay.